Welcome everyone. So today we're going to be looking at transformations of exponential functions. So just before we begin, let's just remind ourselves of what a basic exponential function looks like. And in this case, we're going to be interested in a function that looks like this, e to the x. Alrighty? So let's think about some properties of this. Let's imagine if x gets really big, approaches infinity, what's y going to do? In that case, well, let's say we put e to the 100. Well, that's e times e times e times e times e. That's going to be a hugely big number. And so we can think that as x goes to infinity, y will also go to infinity. But we also should check the other extreme, which is what happens when x approaches negative infinity. What happens as this happens? Well, e to the negative 10, let's just imagine we did this, e to the negative 10, well that's just equal to 1 over e to the 10, right? That's a really small number. And if I make that e to the negative 1,000, well it's going to be 1 over e to the 1,000, which is a really small number. But it's not a negative number. So y doesn't approach negative infinity. No, that's not what's happening here. It actually is approaching 0. Why? Because exponentials have asymptotic behavior, just meaning that they approach some kind of horizontal line. In this case, this function approaches 0. So the only other interesting point is our intercepts, but we've already seen that it approaches y equals 0, but it never gets there, meaning it's not actually going to have an x-intercept. Remember, x-intercepts happen when y equals 0. So the only other place that could happen is a y-intercept, which is when x equals 0. Well, then we would get e to the 0, which is just 1. And so these are probably the three most important parts about an exponential function that we can think about. We have that at x equals 1, it intercepts there. As x is really small, it approaches 0, and then as x gets bigger, so too does the function. So this is e to the x. The main interesting part about e to the x then is that at x equals 1, well, this would be 1 e to the 1, which is just e. So it's growing by a rate of 1e every 1 along the x, in the sense of multiplication. So then you'd get e squared, e to the 3, so on and so forth. Alrighty? So let's think about how we could transform this thing. But in our heads, I just want you to keep really this shape. The shape is going to be the important part to play with. So let's begin playing with this shape. So there are some basic transformations that we can do. One is a translation, where we're just basically moving it from its basic position up, down, left, and right. So let's have a think about translations. Now there are two types of translations. We have horizontal and vertical. So horizontal translations are based on f of x becoming f of x minus b, which means that e to the x would become e to the x minus b. So that will move you b to the left, b units left or right. Vertical translations work much the same. So vertical translations work by f of x becoming f of x plus c. Well, that means e to the x would become e to the x plus c. So with that in mind, whenever we see this addition happening, if it's a horizontal translation, it's like a slide happening left to right. It's not changing the asymptote. Notice the asymptote would still be at 0, y equals 0. But with a vertical change, you would see that the asymptote would get dragged along with it. You imagine if it was shifted down a bit, the new asymptote would be along here. Maybe this is -6 or something, depending on what your axes are set up as. Alrighty, so those are translations. You can go horizontal or vertical. Let's have a look at reflections. Alrighty, so for x-axis reflections, it is in the form of f of x becoming negative f of x. Reminder, this is because in order to reflect something along the x-axis, a point's y-coordinate needs to change, not its x-coordinate. So that would mean that when we're looking at e to the x, well, e to the x is going to become negative e to the x. right? The negative just goes on top. So if the original function was this, well, an x-axis reflection is going to look like this, meaning the asymptote is still the same, but instead of increasing, it's now going to be a decreasing function. So this would be minus e to the x. A y-axis reflection, on the other hand, looks like f of x becomes f of negative x, meaning e to the x is going to become e to the negative x. And a y-axis reflection, rather than looking like this, after reflecting against the y-axis, is going to look like this instead. It's still going to have an asymptote at 0. However, it is going to be decreasing in a different sort of way. It's going to be sort of a sloped down decrease rather than a curved over decrease. Alrighty, so this would be e to the negative x. Alrighty, so those are our reflections. And then all we're really left with after we've done our translations and reflections is the third type of transformations, which is dilations. Alrighty, so dilations come in two different types. We have vertical and horizontal. Swap the order, because everything else I've been doing has been horizontal first. So for a horizontal dilation, we are going to get f of x becomes f of bx, or in this case we're going to use kx. Alrighty, so for a horizontal dilation it's going to look like this, but when we actually do this f of x, we get e to the x becomes e to the kx. Now in this case, this isn't a dilation in the horizontal direction or on the x-axis by a factor of k. It's actually a factor of 1 on the absolute value of k. The reason we do the absolute value is that the reflection part of it would be if it's negative or positive. It changes whether it's been reflected. But it's going to be 1 on k, absolute value, just ignoring the sign of it. And for vertical translation, it is just f of x becomes a f of x, meaning e to the x becomes a times e to the x, or just a e to the x, like so. And this is by a factor of a. Now when we talk about dilations, I think some people have a bit of trouble visualizing what it means. So let's try with the aid. So a horizontal dilation is going to look like a stretching in one of the two different directions. So, oh, it's not gonna, is it gonna let me do naughty? No, it's not. Alrighty. When in doubt, use Desmos. Okay, so I've created a function here, a e to the kx, and a and k are both equal to 1 at the moment. So let's play around with a. So a vertical dilation is going to stretch it in the vertical direction. So as I increase a, it is stretching going upwards and downwards. So let's take an example, right? When we started, what was one of the interesting points of this function? It is this point right here, 0, 1. And as I increase it to say 4, well 4.4, you can see that this intercept is changing as well. Alrighty, let's have a look at playing with k. Now as I increase k, it's actually going to work in the inverse, right? Because it's 1 over k. So as I increase k, you can see it's actually getting contracted towards the center. And as I pull it away, it's actually getting stretched out. So it's getting further away. And so if I do say to the factor of 2, well, then a point that was a little bit further away is going to get a little bit closer, and as I get smaller and smaller, you can see that it's going to stretch out and get a little bit longer. Alrighty, so those are our transformations. Highly encourage you to have a play around with on Desmos just to make sure you're feeling really comfortable with it, and then we're going to move on to actually trying to sketch some of these graphs.